I think I have to start with a little confession. This is my first time at London Calling, so it's a bit weird to find myself up here. But yeah, I'm really excited about what I've seen over the last few days, and there's a lot of amazing work going on. So, well, hi, I'm Seb. I'm from Melbourne in Australia. My only conflicts are potentially full-time employee of VCGS, and Oxford Nanopore supported my travel here to London. VCGS is not-for-profit, wholly owned subsidiary of the Murdoch Children's Research Institute in Melbourne. And we are located, and very lucky to be located, at the beautiful Royal Children's Hospital. Fully clinically accredited genomic diagnostic laboratory. And also quite lucky we are integrated with the Clinical Genetics Service, so we've got a lot of expertise and great people to draw on. And like the meerkats we happen to have at the hospital, we're kind of always on the lookout for something new and what's going on out there, with our focus on translation. In a nutshell, we've been at it for a while, and we are a germline laboratory primarily, so we have access to a lot of different technologies, spanning all the way from traditional chromosome karyotyping to the newest technologies that are out there, which really gives us a lot of good ability to try and solve quite complex cases. And as I mentioned, part of what we're doing is trying to bring these new technologies into diagnostic practice. So we have the ability to develop and validate what's called in Australia in-house IVDs, or lab accredited tests in the US, and therefore bring these technologies into fully accredited clinical practice, which is really something where my passion lies and that I really enjoy doing. Now, being where we are, the question of how do we and what do we do with long-read sequencing was really only a matter of time before this came up. And obviously I'm here because I'm very enthusiastic and excited about it. Otherwise you probably wouldn't have asked me. But when I'm to explain to people why I'm so excited about it, I'm always refer to this little analogy here. And if you compare diagnostic genomics to the challenge of lighting up the best cricket ground in the world, the MCG, at dusk, and you do that by short-read sequencing, it's like trying to do that with like a million little torches. That's what short-read sequencing is like. And then the promise of long-read sequencing is really like we're turning the lights on, and all of a sudden we can see everything. And we've heard a lot of amazing presentations already that are really starting to confirm that. But again, you are here because you clearly believe the same thing. So I'm going to actually jump straight into a specific example of why I believe that this technology will fundamentally, and already has fundamentally, changed the lab, the way that my laboratory is actually working. So this is a case that was referred to us, a little 7-week-old girl with congenital heart disease and non-compaction cardiomyopathy. So she was quite unwell, went into ICU. She was referred to us, to our acute care genomics project that is led by my dear colleague Zanitza Stark, that is also co-leading the research group at MCI with me. And she went into our ultra-rapid short-read whole genome sequencing program. So she was referred, there was a clear indication of a dominant genetic diagnosis. Her mom was also affected. So the sample came in, and within a couple of days, we got this result. It's what I would call intriguing. It's clearly a big deletion. So as far as the little girl was concerned, this is a clear diagnosis. You don't have to be a curation expert that you know this gene is not going to work. It's not there anymore. But what is unusual here is that there's really an indication of there being 2 deletions with a little bit left in the middle. And that's something we couldn't quite explain. That's not something that normally comes across. More importantly, it looks de novo. So mom is supposed to have the same thing, and that really didn't fit what we expected to happen in this particular case. So at this stage, the analyst, Paul, actually got one of our bioinformaticians, Kat Bell, involved. And Kat is kind of our complex case super sleuth. We always refer to her when there's something weird we see we can't quite solve. And they started digging into the data. And yeah, it turns out if you look at the mother's data just right and squint from the right angle, you can kind of see one read that indicates she also had some, the mutation or the variant. So that's actually thought, okay, maybe she might be mosaic. And this case is probably about 3 or 4 years old, as we did back then. We then went through the process of building a confirmatory test, ordering primers, trying to actually confirm this particular variant in this case. In this case, we did that by long-range PCR. So there's a zoomed-in version, so she's also got a couple of split reads, but there was really not much data there. But when we did the long-range PCR, she was actually confirmed to indeed have presence of that large deletion in her sample as well. Now, it didn't tell us, really, it's not quantitative, didn't tell us how much is there. It really wasn't quite consistent with her also being quite significantly affected. And at that stage, the options were kind of, yeah, let's do whole genome sequencing again with high coverage, which is expensive, or do long-read sequencing, which was also expensive. So we did neither of that, rather than give it back to Paul and Kat. So they dug through a little bit more, and they found something else. So in addition to that one read there that indicates a large deletion, they also found these split reads there. So it looks like mom has a separate, smaller deletion exactly in the area where the other deletion in the child, in the proband, has unusually high coverage. Really made no sense, but we did the thing again. We ordered some more primers, we designed a new assay, we did Sanger sequencing, and alas, the short deletion is there, and that is what actually explains mom's phenotype. Now, this is what I would call a truly complex genetic scenario. Both cases are explained. We've got not really any idea of how it got from one mutation to the other. Is there anything to do with it? We don't know. But for now, we've got a diagnosis, which was exciting. Fast forward a little bit of time, we finally got access to long-read sequencing. This was an obvious case to put on. And alas, if you look at the long-read data, this becomes extremely clear. The large deletion is in the proband, no indication of the small deletion in the top panel there. Mom's got a couple of reads of the large deletion, confirming a mosaicism, and it's got the small deletion present in many, many reads. This was obvious, and we could have saved ourselves a lot of time if we had had access to that technology right from the start. It would also have replaced a whole battery of other tests that we needed to do to confirm this ultimate diagnosis and fully crack the case. Now, another example is this particular case, where this was another acute care case of a male child with microcephaly and deaf delay. And through a tool called Schism, which is designed to look for structural variants in short read data, Kat Bell again came up with something that looked a little bit awkward in that gene of MECP2. So we dug through that a little bit further, and using a combination of the short read data and RNA sequencing, she finally figured out that we had a retrotransposon insertion in the last exon of MECP2, and thanks Kat, she makes quite some really explanatory graphics, that disrupted the splicing of that particular last exon in the gene in about just under half of the transcripts, and actually, again, solved that case. Again, eventually we got long-read sequencing data for this particular case, and this large retrotransposon, in this case just about 2.5 kb, was beautifully sequenced through. Once you look at it, immediately obvious you've got the full sequence, and that would have made our life a lot easier. So this is summarizing, again, weeks worth of work and digging with something that would then have quickly replaced the answer. And there's many more examples like this. Another case where our repeat expansion caller for short read data, Stripey, indicated a repeat expansion in DMPK. You do this on long read sequencing. The repeat expansion is there, obvious and very well sized. And we've heard a lot about phasing already. And yeah, yesterday I had a discussion where I said, well, I might be old school, but I think the best way to phase is to actually sequence trios and sequence the parents as well, and was promptly accused of cheating. But I fully acknowledge that there are scenarios where trio sequencing is impossible, and scenarios like this one, where we actually ended up with a second hit de novo variant in a recessive gene, which unless you phase it, you can't prove that it's in trans and make the diagnostic, which is in exome data obviously difficult. Alas, we've heard a lot about phasing on nanopore data is really quite straightforward and easy. So that's what we did, and again, solved the case. So this is just a range of examples that we've encountered in our laboratory where if we had had access to long-read sequencing technology right from the start, it probably would have made these cases a lot easier to solve and a lot quicker to solve. Now, ideally, we would have long-read sequencing for everybody as a first pass. That's admittedly well, it has a lot of advantages in terms of visualization, trying to find these complex events, and also can help problems that are otherwise really intractable, because sometimes none of the alternative assays can actually help us crack a case. It also has got the promise of replacing a whole battery of otherwise quite complex confirmatory tests. The problem is obviously that whole genome sequencing on long read is quite expensive, especially if you're just trying to use it as a confirmatory test of something you already expect. And that is on a context where there's actually, at least in our laboratory, increasing demand for these confirmatory tests from ever-improving bioinformatics methods on short-read data and from also from projects that now routinely reanalyze the data. So the obvious solution for us was adaptive sampling. And I've got a few more examples of how that really became in handy. So I mentioned reanalysis. This is really something that we've encountered a lot based on a project that is, again, led by Zornica, that developed a pipeline called Talos. And Talos does one thing, which sounds very simple. It goes back and reanalyzes all our negative genomic cases every month. In this particular scenario, it also introduced a new tool, which was a CNV call on exome data, which wasn't called on these data sets. And all of a sudden, we ended up with a raft of samples where we had unconfirmed exome copy number variants that then needed to go through orthogonal confirmation so we could report them clinically. And we try to do that with a range of different technologies. Again, high-resolution arrays. Obviously, doing genome sequencing would have worked, but that's a very expensive way of doing it. So we decided to use adaptive sampling for these cases, and alas, again, the answer was very clear. And in this case, we could do it quite quickly, and in that stage, it also becomes cost-efficient. And there's many other examples of that happen. This is another deletion. This is admittedly not quite as clean, but it was also made on 6-year-old archival DNA. So one thing I haven't mentioned is we didn't do anything fancy to any of these samples. All the long-read data I've shown is run of routine diagnostic DNA that runs through our routine automated extraction. There's no special care taken for long-read, and we still get extremely good, useful results that help us ultimately solve our cases. Now, in the second case in particular, it shows that it doesn't always work, because we had a second variant that we would have liked to face that didn't quite work. And here's another example where we had, again, the same scenario again. We had an acute care case where we had a recessive candidate variants in the Titin gene, where one of them was de novo. Now, unfortunately for us, Titin is literally the largest gene in the genome. These two variants were about 153,000 kilobases apart. And despite the phasing callers, because it always puts stuff into phase 1 and phase 2, it looked like they were properly phased. Once we look at the phase block, it turns out there was a massive gap, and we could actually not span across it. So there's, I think, well over 50 or 60 kb in where there was just no informative markers for the tools to do anything with. And yes, I'm sure if we had longer reads and better DNA, we may have gotten across it, but this was a sick child in ICU. We just didn't have that, and we didn't have the process and time to do it. What we did have was the short-read data from the parents. So therefore, what we could do is we used the short-read data, we actually developed the genotypes of the parents, and then we could use the long-read data to resolve that case. And not only did we solve, achieve a genetic diagnosis for this child, we also, instead of spending 2 months on this, unlike the last case, we managed to do this in an 8-day turnaround time from receiving the sample, getting the short-read data, solving the case, and that was all the Christmas and New Year period. This is fast, and this is informative. So this is really something that will really help change how we do this type of testing. Now again, it doesn't always work that easily. This is a case where we had another very complex scenario of a part of the PKD1 gene that, as Kat determined, got deleted and inverted and inserted somewhere else in the exome. Now, if you look at the short-read data on top, it's blatantly obvious that there's something not quite right. In the long-read data, that's not clearly as visible, because the long-read data actually shows us what's really going on in the genome, whereas the short-read data kind of shows us what the curators are expected to see on short-read data. So there's a few challenges that we still need to overcome to not fall down the traps of missing these types of variants and these types of cases. And there's a question, what's better to know? Seeing something that shows you obviously something is wrong without knowing what it is, or knowing exactly what's going on and then being able to interpret it. I mean, I clearly lean on the latter side. I always like to know what's going on. But there is challenges in getting people used to seeing and working with this kind of data. Overall, we've now done several dozen of these cases with adaptive sampling, a whole range of different applications and technologies that we really applied this to, from many small deletions in a whole range of different genes. And you can see here, some of them confirmed, some of them didn't confirm, but that's fine. Because we want to know whether what we're looking for is real or not. So not confirming a variant means there's nothing more to look at, and we don't have to waste many more months in trying to chase it and seeing if it's real or not. If it's not confirmed, it's not real, we can move on and trying to find a different diagnosis. We've got other examples of repeat expansions. We've got complex inversions. We're even now starting to use adaptive sampling to try to look for methylation-based data. So there's another case with an MECP2 presentation that was unusual. So we had a theory of skewed exon activation. Again, it didn't turn out. But the point is, from the point we had the idea, it only takes us a matter of days to make a bed file, to put the library on the nanopore sequencer, and we get a result. So it's a really quick way of resolving these type of conundrums. And again, as I said before, it's not actually as expensive as you think anymore, because while Sanger sequencing is admittedly cheap, but you still have to design the primers. You still have to optimize the assay for every case. You still have to spend a lot of labor to do that. I don't know about you guys, but in Australia, it takes us a week or two to even get the primers once they're synthesized. So there's a lot of delays that we have to account for, and this is where this, the concept of adaptive sampling really makes a difference to how fast we can turn them around. This is so easy now that in our laboratory it's almost become a running joke that every time we see something we can't do, we don't understand, we can't deal with. In the past we said, okay, now we need to do this assay in MLPA and we need to design that and maybe then we try that. Now we say, well, just put it on the nanopore and next week we know the answer. It makes a real difference and it's something that is here right now. So in summary, long-read sequencing can provide a clearer picture of many complex genetic events and really has the potential to replace a whole range of otherwise quite cumbersome and at times quite expensive orthogonal diagnostic tests. And that is without even doing long-read whole genome sequencing. As I said, if I could do that, it would be great, but right now we're not there yet. But it really then, it supports a very wide range of potential diagnostic applications, once accredited, and can be used, as I said, in a time and cost-effective way. So there is a lot of strength in what this can do, and as far as I'm concerned, we should be using this in the diagnostic setting right now. Quite frankly, I don't quite understand why people don't have it. Now, caveat, of course, RU or only, but if you happen to be lucky and work in a lab like ours, where you can do your own in-house accreditation and do an in-house IVD, I think this would be a really good thing to look at, even without necessarily going straight to long-read whole genome sequencing. So I'm clearly a fan of adaptive sampling and long-read sequencing, and as I said, for us, it really is already starting to fundamentally transform the way we work. Now, let me say thank you to the key people that were involved in that. I've already pointed out Zonitza and Kat Bell. But we also got Simon, who is our lead clinical bioinformatician and wrote the Stripey tool. Sebastian is really doing the vast majority of our bioinformatics nanopore analysis. And congrats, Sebastian. His family just had their first child, so good on them. Paul was one of the analysts and is a curator in my team. Andreas Hallmann has written the Stripey tool. And Simon is the person that is doing and has done a lot of the lab work, both for the confirmatory test and now for the nanopore. And I think there's no high price for guessing which technology she prefers. With that, I thank you for your attention.